Okay, so what we're going to look at today, we're going to look at another way to solve quadratic equations. So we think about what we've done so far. We looked first week. We looked at. Why don't you go ahead? I need earbuds out. I need those things closed up. I need everybody with me here. I'll try to make it up to you. I'll tell you what. I know I owe you. I owe you some work time. I'll find a way in the next week to build that back in for you. Like I say, I apologize. I just forgot to tape this, so we're kind of stuck. It's my bad. I think what we did last week, we solved quadratic equations. We practiced factoring. We ended up solving quadratic equations by factoring when we had binomial factoring patterns or we had trinomials, right? Today we're going to look at another possible route we could take. And our goal here, keep in mind that by the end of the unit, our goal is we're just going to solve quadratic equations in the best, meaning the simplest way possible. So here's another possible route we can take to solving quadratic equations. Okay, let's think about this one here. How could we solve this? Okay, it looks kind of like a mess, right? But we could do this like we did last week. If I were to take this expression that's being squared, this 3x minus 4, and I were to square that, think what that would look like. It would be the quantity 3x minus 4 times a 3x minus 4, and I would have to FOIL all those things out, right? It'd be a little bit of a process. I'd have to FOIL it out, collect like terms, and when all the dust had settled, when I FOILed that out, I would end up getting an x squared term, right? I'd get a term, an x term, and I'd get a number. And then from all that stuff, I would subtract 5 and it'd be equal to 76. We're not going to do all that stuff, but we could, right? We could multiply all this stuff out. And what if when we expanded everything out, we FOIL this out, what if we just collected all the like terms and subtracted 76 from both sides? Okay, that's a lot of stuff to do. And I'm not going to take you through that. We're going to have a better way of doing this. But when I did all that stuff, I would end up with something like this, right? I would end up with something like, we don't know what the number would be, but it'd be, call it A times x squared, plus some number times x, call it b times x, plus some number equals 0. So we'd end up with a quadratic equation in standard form. And then maybe if it factors, we could solve that like we did last week, right? We could maybe break this apart into factors and use the zero product property, okay? All that stuff could potentially work, okay? There might be an easier way though. Let's take a little stroll down memory lane here. Let's go back to the beginning of the year. Think what we did when we were just reviewing linear equations at the start of the year. I told you guys something, and we haven't really practiced this for a while, but I told you something. I said if you can ever point to a single x, you can always solve for it by isolating it, right? You can isolate that single x by just reversing order of operations. If you can ever point to a single x, that worked for linear equations, and it turns out it works for quadratic equations. Well, how many x's do you see in this equation? 1, right? I can already point to a single x right there. So I should be able to use inverse operations to isolate that thing, right? Now, we're going to start this problem and then we're going to stop. We're going to get to a point where there's something that pretty obviously we're going to need to get some practice on, and we're just going to stop this process. We'll pick it up again on Wednesday, and we're just going to practice, kind of review a skill from Algebra 1, and that's really what today is going to be. But let's start at least. So if we use inverse operations, right, that's just the opposite direction of PEMDAS. Start at the bottom and work our way up. And that's the direction we go if we want to isolate a variable or solve, right? Same thing. Isolating a variable is the same thing as solving for that variable. So keep in mind here that when we use inverse operations, we don't get to parentheses or grouping symbols until the very end, right? So we see some parentheses here. There's some parentheses enclosing this quantity that's being squared. We don't get to deal with the stuff in the parentheses until we've worked all the way up through inverse operations, right? So then when we see stuff like add or subtract or multiply or divide, we're talking about things that are outside of the parentheses, right? So what's our first step going to be then? Step 1. Is there any addition or subtraction outside of the parentheses we need to get rid of or undo? What is it? Okay, so we got to undo subtracting 5. Well, how do we do that? Add 5 to both sides. Okay, good. And that's going to give us the quantity 3x minus 4 squared equals 81. Is there any multiplication or division for me to undo outside of parentheses? No, there isn't, right? There's nothing. I don't have to divide both sides by anything, so I can skip that step. Okay, are there any exponents to deal with? Yeah, aha, okay, this is different. Now we've got an exponent there. We've got a squared. How do you suppose we're going to undo a squared? Square root, exactly, right? We're going to square root both sides. Okay, so sometimes we can, if we can point to a single x in a quadratic equation, we can isolate it oftentimes by just using inverse operations, including a step where we have to square root both sides. It's called the square root property, okay? Okay, so we need some practice with that. And that's what we're gonna pause this process for today and just remind ourselves, a little review, how do we square roots? Okay, and there's a little bit to it. First step of simplifying square roots has to do with writing numbers in their factored form, prime factored form, right? A prime factor is a number that you can't divide by anything other than itself and 1, right? So how do we factor a big number like 2520? There's a number of ways that you can write this down, but I think a really good way to do it is using a factor tree. Do you guys remember factor trees from way back in the day? You may not. I see some nods here. Some people kind of vaguely remember this process. With a factor tree, we start with the number, and then it's going to branch out, and we're just going to divide it into 2 numbers. We got to come up with 2 numbers that multiply to 2520. Okay? Is there one right way to do it? No. And you can divide it a bunch of different ways, but ultimately, we're going to end up with the same answers at the bottom. We're going to branch these things out until we can't go any further, until we get prime factors. We're going to get the same prime factors no matter what. So what are 2 numbers that multiply to 2,520? And a good way to think about that is, can you think of a number that divides into that evenly? I'll give you a hint though. If it ends in 0, that's 10, right? Any number that ends in 0 is divisible by 10, isn't it? Right? So we could split this up. You don't have to do it that way, but it's a good, convenient way to do it. So we could split this into 10 times 252, right? So we got 2 branches now. We're going to see if those numbers branch. What does the 10 branch into? 2 and a 5. And those are prime, aren't they? I can't go any further with those. So we're done. That branch is done. How about the 252? We just got to come up with at least one number that divides into 252. Okay, so we know it's even, so we could break this into 2 and 126. Okay, what about 126? Okay, 6 and 21 you said, right? Okay, how did we know that works? How do we know that 6 divides into that? I want to go through a couple little tricks with you here today about these divisibility tricks. And these aren't really algebra type things, but you may have never learned these. And there's some pretty cool little tricks that help you know what numbers divide into something. Okay, how do we know that 6 divides into this? Well, we know 2 divides into it because it's even, right? If 3 divided into it, if both 2 and 3 divided into it, 2 times 3 is 6. So I would know that 6 would divide into it, right? We know 2 does. How could I check to see if 3 divides into that? Do you know a trick for that? Anybody know a trick for that? How do I know if a number is divisible by 3? Well, okay, but what if it's a really huge number and you don't want to go through the process of having to divide it all out and then find out maybe it doesn't work? There's a trick so you can always know if 3 is going to divide evenly into a number. No, because like 16 is not divisible by 3, right? There's a good way. You think you got it? What? Okay. That's a good way. You could deconstruct this thing. That's good thinking. There's even an easier way to do this, though. Maybe you haven't heard of this trick. This is a great trick. If you add up the digits to any number, if the sum of the digits is divisible by 3, then the entire number is divisible by 3. Okay, that also works for 9, by the way. So, like, I could add these up, and 1 plus 2 plus 6 is 9. 9 is divisible by 3, and so therefore the number is divisible by 3. But we can even go one step further, and we can use that trick for 9. I could break this up into, because 1 plus 2 plus 6 equals 9, that's divisible by 9, so I could divide 9 into this. How do we do that? Let's go through that process too. How do I divide 9 into a number like this without having to write down big, long division problems? Say we don't have a calculator right now. You can always just do long division in a tabular way. We can just kind of keep track as we go. Does 9 go into 1? No. So we scoot over a digit. 9 goes into 12. How many times evenly? How many times does 9 go? It goes in once. So our first digit is a 1. 9 goes into 12 once with how much remaining? 3. So I'll put a 3 up there and move to the next digit. 9 goes into 36 how many times? 4. Evenly, right? Okay, with no remainder. So I get 9 and 14, and both of those I can break down into prime factors, right? 9 breaks down into 3 and 3, good. And 14 breaks down into 2 and 7, right? So now I've got this, notice the red ones are the prime factors. So I've got this thing broken all the way down to where I can't go any further. They're all prime factors, right? Okay, so then what's my answer look like? We want to organize our answer. In math, we always want to be as organized as we can because it makes it a lot easier, right? So when we're writing a number in prime factored form, we'll start with the smallest prime factors and just work our way up. Well, we have some 2's. How would I write 2 times 2 times 2? 2 cubed. So I'm getting 2 cubed times, what's my next biggest prime factor? Oh, what happened there? I have no idea what that just happened there. Oh, it crashed on us, of course. Why not? Okay, where were we? Oops. That wasn't us. Okay, that was us. Yeah, she did it. Write it down. Oh, well, we almost got it. It didn't save the whole thing, but we were close. So we said that broke down into 3. Two and 7. So then our final answer just looks like 2 cubed, because I've got 3 factors of 2 being multiplied, times 3 squared, because I've got 2 3's. It looks like then my next biggest is a 5, and I've only got one of those. And then I've only got 1 7. So that's how I'd write out my answer. Okay? All right, so there are, okay, what about something like this? Okay. how is this similar to the last problem? Well, you wouldn't know that it's similar, but there is a connection between these. If I'm trying to simplify this radical, it has to do with the way that number factors. Do you guys remember learning the trick? Couples go out, singles stay in. You remember that a little bit? Okay, so give me a little show of hands. How many people remember doing that? Ooh, okay, maybe sort of, tiny bit. We're obviously going through it. So here's how it works. We want to take the number that's inside the radical, and we want to break that up into factors. Okay, our goal, by the way, whenever we're simplifying a radical, our goal is always the same. Our goal is to get as much of the number out in front of the radical as possible. Right, that's our goal. We still may be stuck with some stuff that's inside the radical. We want to get as much out as we can. So we start off with our number, 4410. We're going to make a factor tree. So what's one number that obviously divides into that? 10 does. Good. Okay. So we get 10 times 441. Okay, the 10 we know is going to break up into a 2 and a 5. What about that 441? Can you find a number that goes into 441? 3 does, and 9 does, right? Because 4 plus 4 plus 1 is 9, and 9 is divisible by 9. Okay, so we know 9 goes into it. How many times? Well, 9 doesn't go into 4. 9 goes into 44. How many times? How many? I heard it, 4, right? 4 times 9 is 36. What's 5 times 9? 45. That's too big. So it doesn't go in 5 times. It goes in 4 times with how many left over? 4 times 9 is 36. So 8 left over. 44 minus 36 is 8. Scoot over to the next digit. 9 goes into 81. How many times? 9. Okay? And 9 splits up into 3 and 3. 49 splits up into 7 and 7, right? Okay, so then what do we end up getting? So if we want to write this square root as the square root of a whole string of numbers that are written in as factors. Okay, what do we got? We've got a 2, it looks like. We've got a 3 times a 3, so that's a 3 squared. And then we've got, it looks like a 7 squared. And a 5. Whoops, not put a plus there. I don't want to put a plus. Times 5. I didn't see the 5. Times 5 times 7 squared. Okay, why is that helpful? Okay, there's a little property we're going to use here of radicals. We can always take the square root of a product and we can split it into separate square roots. So anytime I have a square root of a times b, for example, where a and b are just numbers, let's say, I can rewrite that as the square root of a times the square root of b. And if there's more factors in there, I can split it into more products. So I can break this into a bunch of individual square roots. We're not going to do this. You can skip all this stuff in the future. I just want to show you why this works. So this gives us the square root of 2 times the square root of 3 squared times the square root of 5 times the square root of 7 squared. Do you notice anything good happening there? Do you see anything important happening to any of those radicals? They're different colors. Okay, what do you mean by 2 of them are prime numbers? Okay, those can't be square rooted. What about the square root of 3 squared? What's that? Okay, that's 3, isn't it? Right? That's the square root of 9, which is 3. But we don't even have to square out the 3 because we know, you already told me, that square roots and squares cancel each other. They undo each other, right? So right away, we can see that square root and that squared, they undo each other. This square root and squared undo each other. And look what we end up getting then. we end up getting a 3 that doesn't have a radical times a 7 that doesn't have a radical times some numbers that are stuck in the radical, right? The radicals didn't go away for those. So inside, I get a 2 times a 5. Okay, well, we didn't even have to go through that process if we just remember this little saying. Couples go out, singles stay in. So when we get our radicand, that's the fancy name for the number that's inside the radical. Whatever the number in the square root is, inside the square root, when we write it in factored form, here's our trick. Let's go ahead and just, it doesn't matter if you put circles or boxes. We'll just say we're going to put circles around couples. What's a couple? A couple is just a pair of identical factors. So look, we get a couple of 3s, and I get a couple of 7s. And let's put boxes around the singles. I get a single 2 and a single 5, right? So then we know that the couples go out. So the couples are going to go out of the radical into the front of the radical. So I end up getting, I had a couple of 3s, and so I get a 3 out front. Not both 3s, just one of them, right? I'm going to write whatever I have a couple of, that's the number that goes out front. So if I have a couple of 3s, I put a single 3 out front. I have a couple of 7s, so I'm going to put a single 7 out front. And singles stay in. So they're staying inside the radical. I had single 2 and a single 5. Everybody get that? It's always going to work that way, okay? So then my final answer, I could just simplify this to be 3 times 7 is 21. Times the square root of 2 times 5, which is 10. Everybody good with that? Does that make sense? Okay, that's our simple trick for simplifying any radical. It could be as big as you want it to be, right? All you got to do is factor it and then use that little saying, okay? All right, so there are some of these divisibility tricks that some of these you know, some of them you may not know. So I'm just going to go through real quick the divisibility rules for the numbers 2 through 10. And you don't have this in your printed notes, but it'll be on the notes that are online because I'll put this PDF up online, okay? So how do we know if a number is divisible by 2? Well, if it's even, right? How do you know if it's divisible by 3? We talked about that. You add the digits up, and then if the sum of the number is divisible by 3, the number is. For 6, it would just be a combination of both of those, right? If a number is even and the sum of the digits is divisible by 3, then it's divisible by 6, okay? We already talked about, we'll skip down here for a second. We already talked about 10. If the last digit is 0, it's divisible by 10. What if the last 2 digits are zeros? What divides into it? 100. And if there are 3 digits, it'd be 1,000, etc., right? We talked about the rule for 9. You add the digits up, and if the sum of the digits is divisible by 9, the whole thing is, okay? Now, the nice thing about that, too, is, I'm going to show you an example of this. You can do this multiple times. Like I could take just a stupidly big number, and let's say I had something like, oh, hang on here. Let's do, okay, what if I had something like this? What if I had a number like, for this rule, what if I had a number like, what is that? 99. I want to know if that number is divisible by 9. I could add up all those digits, right? That's going to give me let's see, got a bunch of 9s there. So 1, 2, 3, 4, 5, 6, 7, 8 times 9 would be 72, plus another 12 is 84, plus, oh, did I do that wrong? Did I do that wrong? I think I did. Hang on here a second. Oh, no, never mind. Plus 18. So what would that be? I'd end up with 1, 2, 3, 4, 5, 6, 7, 8, 72 plus 18. So that's going to be, let's see, I had something like another, make this even a little tougher. Say I had another 9 and a 9 out front. So that's going to give me something like, if I add the digits up, not the number, I'd get 108. Okay. Well, is 108 divisible by 9? Well, say, I don't know. I mean, maybe it's even a bigger number. Maybe I don't know off the top of my head if that's divisible by 9. I can do the same trick again. I could add the digits up again. Well, it is, I know it is divisible, but say we didn't know that. Say we got it when we added the digits up. What if we were talking about some ridiculous number that had like 47 digits in it or something, right? So we get some big number. When we add that up, we get a really big number just when we add the digits up. I can do the same process again. I could take my answer and add those digits up, and 1 plus 8 is 9, and now I know that 9 goes into that, and so 9 is divisible, or the original huge number is divisible by 9. So you can just keep doing that over and over again with your answers if your answers are too big. Does that make sense? I don't want to spend too much time on this. Okay, what about 4? Oh, 5. If the last digit is 0 or 5, we know it's divisible by 5. You probably know that one. What about the rule for 4? Okay, so this is a good one. You know that 4 divides evenly into 100, right? So once we get 2 digits deep into the number, it doesn't matter, because that's just counting the number of hundreds. If I had something like, for example, that's just 137 times 100, isn't it? That's 137 hundreds. So I know that 4 has to divide into that evenly because it divides into 100. So it's going to divide into any number of hundreds. If I change those last 2 digits, though, it's not so obvious. If I make those last 2 digits something like, how about 72? If I want to know if 4 divides into that whole big number, all I have to do ever is focus on the last 2 digits. If it divides into the last 2 digits, it divides into the whole number. Does 4 divide into 72? Yeah, it does. So it divides into the whole thing. It's a good trick, right? Only look at the last 2-digit part of the number, and if that's divisible by 4, the whole thing is. Similar rule applies for 8. 8 doesn't divide into 100 evenly, but it divides into 1,000. So you can just look at the last 3-digit part of some big number, and if that's divisible by 8, the whole thing is. 7's the weird one. 7's a weird one. 7, I mean, you may forget this one, but this always works, and it's crazy that this works. If you take the last digit of the number you're testing and you double it, subtract that from the digit formed by all the rest of the number formed by all the remaining digits. If you take the first digit out, if that new number is either 0 or a number that's divisible by 7, the whole thing is. So let's do an example. Like, what if you had something like, let's make one up here. Okay. So what if I want to test something like 882? I want to know if 7 divides into 882. What are my rules? Take the last digit and double it. What's the last digit? 2. Double it, I get 4. I'm going to subtract that from the first 2-digit number, right? The other digits, 88. So 88 minus 4 is 84. Okay? So is that number divisible by 7? It is, but if you didn't know, we could just start the process again. I could take the last digit and double it. 4 times 2 is 8. Subtract that from 8, and I get 0. So it is. Or I could just know that 7 goes into 84 evenly. It goes in, what, 12 times? Okay. Isn't that crazy? It always works. That one always works. And you can repeat that one over and over again, too. Okay. All right. Those are kind of good like for SAT tests and things like that, where you don't have access to a calculator for the whole thing. All right. Let's try another one. How about one like this? So you guys walk me through the steps here. What do I got to do? Say it again. Okay. So you're saying 8 goes into that? Does it go into 232? It has to go into those last 3. Because remember, it has to go into the first 3 digits for 8, first 2 digits for 4. So maybe let's do 4, right? So we know 4 goes into 32, right? So 4 goes into the whole thing, okay? So we're making a factored tree, aren't we? Four goes into 32. So we know it goes into the whole thing. Well, let's divide it in. 4 goes into 12 how many times? 3. Does 4 go into 3? How many times does it go into 3? 0, right? Doesn't go into 3, so we're going to carry the 3. 4 goes into 32 how many times? Okay, so it breaks into 4 and 308. Okay? What about 308? Does 4 go into 308? It does, doesn't it? Right? Because it goes into the last 2 digits are 08. 4 goes into 08. So I can do it again. Okay? 4 goes into 30 how many times? 7. Okay? 4 times 7 is 28. So what's the remainder? 2. 4 goes into 28 7 times, right? Okay. 77 splits up into 7 and 11, and those are prime, right? But look at this. I got a couple of 4s here, didn't I? Okay, so my final answer, remember, there's 2 parts to this, right? There's going to be the outside part and the inside part. So I got a couple of 4s. Oh, stupid thing. So I got a 4 outside. I've got single 7s and 11s. What's that? What about it? No, okay, good question. Hold that thought. That's where we're going with this. So I could have broken each of those into 2s, couldn't I? I could have done something like this. I could have said, let's break that 4 into a pair of 2s and this 4 into a pair of 2s. But then I would have just gotten a pair of 2s and a pair of 2s. So I would have had a 2 and a 2 out front, which is just a 4. So what's the moral of the story? Do you really have to go all the way down to prime factors? No, we just have to go down until we can see couples and singles. The singles need to be prime. But the couples, if I can have bigger numbers that are couples, it makes my job easier, right? Everybody see that? Okay, so we could have that's why I didn't immediately break this 4 down into a 2 and a 2, because there's a chance I was going to get another 4, so I could have a couple of 4s and just put a single 4 out front. Everybody get that? Okay. All right, what about one like that? When are we out of here? So, oh my gosh, this one went fast. So what about something like this? So I could multiply all those out and turn this into one big square root of 300, right? 2 times 10 times 15 is 300. Okay, but do I want to do that? I don't need to. They've already done some work for me. They've already told me that factors of that big number are 2, 10, and 15. They've already started the factor tree for me, right? So we'll just keep going. 10 breaks up into 2 and 5. 15 breaks up into 5 and 3. And look what we get. Couple of 2s, a couple of 5s, and a single 3, right? So we could write this as 2 times 5 times the square root of 3, because couples go out, singles stay in. So my final answer just looks like 10 times the square root of 3. Okay? What about fractions? Okay, so if we're going to simplify this like we normally would, hey, Mr. Thompson, what's going on? If we're going to simplify this, do you need to see me? Oh, nice.
Special.
Nice. This is great timing because this thing has been kind of dying a slow death. Yeah, they are.
Miss Youngman also got one, so if you need help setting it up.
Nice. Go see. Yeah, I've kind of figured that. So if we're going to simplify this thing using PEMDAS, we simplify just regular top to bottom, right? So parentheses are grouping symbols. Well, all this stuff right here is grouped inside the radical. So we want to start off by asking, okay, could we simplify that fraction? Yeah, 4 divides into both of those, doesn't it? So step 1 would just be, we could turn this into, let's see, 9 over 4, right? Okay, now what? Well, now that's as far as we can go inside. So now we got to break this thing up into parts. Just like we said we could take a square root of a product and separate it, we can do the same thing when we're dividing. If I have the square root of a quotient, I can split that into the square root of the top divided by the square root of the bottom. Okay, so we can do that here. We can split this apart into the square root of 9 divided by the square root of 4, and that just gives me 3 on the top and 2 on the bottom, and I'm done. Okay, agreed? Okay, but what happens if we have something like this where the square root doesn't go away on the bottom? Okay, there's a rule here. We can't leave square roots in the bottom. We have to rationalize the denominator. A way to remember that is no tenths in the basement, right? So we've got to get rid of this square root on the bottom. Think about this. How could I undo a square root on the bottom? Okay, if I were to multiply the bottom by the square root of 7, square root of 7 times square root of 7 is the same as square root of 7 squared. That would cancel the radical on the bottom. But I can't just do that. I can't just multiply the bottom. Whatever answer I got when I typed my original number in a calculator, some wacky decimal, that has to stay my answer. So what's the only number I can multiply something by and not change its value? 1, right? We said that at the beginning of the year. So I've got to multiply by some fraction that's equal to 1. So what has to be on the top? Square root of 7. I have to have the same thing on the top and the bottom, so the whole thing is equal to 1. So when I multiply straight across, then I just get 6 times the square root of 7 divided by 7. That looks actually like more complicated, but to a mathematician that's better because there's no radical on the bottom. Is that all ringing a bell? Whew, that's a lot of stuff. When are we out of here? 1 minute? Okay. I better cut it off right there. All right. Get your desk real quick and then just toss them on the way out. What's that? Over this stuff? It's coming up pretty soon. We'll do, like within a week and a half. Yeah. See ya. Have a good day.